irregular microstructures in GN configurations.
Okay, well, thank you very much for the invitation to talk. Yeah, this is joint work with experimentalist Tomonari Inamura, brilliant experimentalist, and my former student Francesco Della Porta. Now, Francesco very regrettably left mathematics, and now he works for his family firm making salami and so on in northern Italy somewhere, but he still, the weekends, he thinks about mathematics. So. Okay, and now, those of you who were at the program 6 years ago may remember this picture, because it was the one that advertised the program, actually. So it's kind of appropriate to talk about it today. So you may wonder, that was 6 years ago, so why didn't we understand about it then? So I have to confess that I sometimes take a long time to write papers, and this one is actually being written at this moment, finally. So what is this amazing experiment of Inamura? So this is a polycrystal. So here's one grain of the polycrystal. So at a high temperature, the crystal axes of the material were the same in this particular grain. And then in nearby grains, there were different orientations. Okay, so now roughly what we're seeing here is the result of a Martin-Siddick phase transformation, so that when you reduce the temperature through a critical temperature, the underlying crystal lattice changes shape. And it can change shape in different crystallographically equivalent ways, and you may choose different points in the material to change in one way, and they all have to fit together geometrically. Now, this particular microstructure that you see here, so I should say first of all, this is a more sort of raw representation of the bottom left-hand corner of this picture. And the colors here are not real colors, they're post-processed. So from EBSD and other techniques, you determine what the deformation gradient is in each region, and then post-processed it's given a color. And here you see the scale, so 25 microns. So the diameter of this grain is considerably less than a millimeter. Okay. Now you see of course this looks like a two-dimensional picture, but the original situation is three-dimensional. So what he does is he takes a hot wire and cuts through the three-dimensional picture and exposes various grains. Right? Now, the hot wire, of course, does damage to the phase transformation. So then you have to polish off the sort of the top layer where the hot wire was, and then you get this microstructure which is exposed. So it's an incredible, time-consuming, difficult experiment. And there it is. And it's very unusual. This microstructure is very unusual for Martin-Siddick phase transformation. It doesn't usually look like this. Okay, and it's and what's the alloy? It's titanium 76, niobium 22, aluminium 2. So that means 76% of titanium, 22% of niobium, 2% of aluminium. Okay. So now we're going to use a nonlinear elasticity model for this, and I show you the model for a single crystal. So I just look at one of these grains. So we have the crystal in its reference configuration omega, some bounded region of R3, and the deformation of the crystal is given by a map y from omega to R3. There's no time in this theory, unfortunately, so it's entirely static. And the bulk free energy at temperature theta, so theta is the positive temperature, is given by integrating some free energy density that depends on the gradient of y, so you can identify that with a 3x3 matrix actually with positive determinant, so you don't have reflections and so on. And the psi is what determines the material, that's the free energy density, so it depends on this 3x3 matrix and the temperature. And so we're going to assume that a phase transformation occurs at theta critical, and that the crystal lattice is cubic for temperatures bigger than theta critical, And we're going to represent some features of the phase transformation by looking at the set of minimizing matrices at different temperatures. So K theta is the set of matrices with positive determinant that minimize the energy density at temperature theta. Okay, and here we have these three different cases when you're bigger than theta critical, less than theta critical, or equal to theta critical. So maybe it's easier to look at the one where you're equal first of all. So now we're going to take the reference configuration to be the cubic phase at the critical temperature. So then a minimizer should be given by the identity as a y of x equals x, which has the gradient, the identity matrix. So the identity matrix sits in SO3, it's a set of rotations. So why is it SO3? Because this function is reasonably supposed to be invariant to multiplying by rigid rotations on the left. That's frame indifference. So this SO3 here is the cubic, is an energy well corresponding to the cubic phase at the temperature theta critical. Now we have the change of shape of the lattice, which is given by capital N positive definite symmetric matrices. And they're all got from a single positive definite symmetric matrix, U of theta, and they're got by operating by matrices Q on the left and Q transpose on the right, as Q runs through the cubic group, which is the group of rotations of a cube. There's 24 such rotations, which is why it's called P24. Now, when you do this, as Q runs through P24, you might think you get 24, well, you do get 24 matrices, but some of them can be the same, okay? And so this number n here, actually by a bit of group theory, has to divide 24. Okay, so at the critical temperature that you have these energy wells, one corresponding to the cubic phase and n corresponding to the low temperature phase. Now above the critical temperature, you have just the cubic phase. This is just a thermal expansion coefficient, which we make to be 1 at theta critical. And below the critical temperature, we want the transformed phase to minimize the energy. And so we have a bunch of these energy wells now with UI evaluated at the temperature theta. Okay, so we're going to assume that. And now, this particular alloy, it undergoes a cubic to orthorhombic phase transformation, and theta critical is about 434 degrees Kelvin. And now for theta bigger than theta critical, it's a BCC, that's body-centered cubic, solid solution. So if I look, for example, here's a cube of the lattice, so there's an atom at each corner and one in the middle. Now all these atoms are equivalent, so you can think of any atom as being either a corner or one that's in the middle, right? Because it's a Bravais lattice. Now, saying it's a solid solution means that each lattice site has a probability of being occupied by a titanium or an niobium or an aluminium atom, and overall the percentage has to be so that you get the concentration 76, 22, whatever it was, 2. Okay. Now, what does the change of shape involve? Well, in this case, let's look at the reference coordinate, orient the reference coordinates like this, so x1 horizontally and x3 coming out of the screen. So one of the ways to represent the change of shape is that you have a stretch by beta in this direction. Okay, so in this direction you have a stretch by a factor beta, and then you have stretches of magnitudes alpha and gamma in the perpendicular face diagonal directions. Okay? So then this object here, which is dotted, becomes this orthorhomb, if you like, for theta less than theta critical. So we could have chosen any one of these three axes because we have cubic symmetry, and then you get different. So you will get, you see, 6 possibilities. You have 3 choices for this axis in which to stretch by beta, and then you can swap the other 2 directions. Okay. So now, here's a slightly puzzling thing. These are the various temperatures involved. So now, actually you have hysteresis in this alloy. So theta critical is 434. That's where the two phases have the same energy. But you need to reduce the temperature further than that to 408 Kelvin in order that the martensite, the low temperature phase, so the low temperature phase is called martensite, the high temperature phase is called austenite. So, so you have to go lower than 434 to 408 before the martensite starts appearing. That's the martensite start temperature. And then you continue reducing the temperature, and only when you get to 314 has it entirely transformed to the martensite. Okay. Now you go back. Okay, you start heating up, and something very odd happens, a bit puzzling. So the austenite starts appearing at 375, which is less than 434. So why on earth should it start transforming to something which has higher energy, right? Because at 375, the austenite has higher energy than the martensite. Now, that's because actually, when the martensite forms, it doesn't form stress-free. So it's stressed, and so this sort of simple energetic argument doesn't apply. In any case, then you have to, at 375, the austenite starts appearing again, and finally at 460, which is above 434, it's entirely in the austenite. And theta C is traditionally estimated as a half of ms plus AF. Okay, so there's the transformation. So beta in one direction, and then alpha and gamma in the perpendicular face-centered directions. Alpha and beta and gamma depend on theta, and they're positive. And here we've got 6. N is 6, which divides 24. And here are the 6 variants, and you see 2 of them will have beta in the 3 slot, 2 of them will have it in the 2 slot, and 2 of them have it in the 1 slot, and the other ones you just swap the signs of alpha and gamma. You just swap alpha and gamma. So there we have these 6 variants, and the lattice parameters are experimentally determined to be alpha, which is 1.03, beta, which is 0.9699, and gamma, 1.0003. Okay? And they're measured actually at ms, and so there's some slight issues there. Okay, anyway, what we see is that this one is incredibly close to 1. Okay. Now, the middle eigenvalue then is almost exactly 1. And I'm going to assume that it is exactly 1. Okay? Now, why is the middle eigenvalue being exactly 1 important? But before that, I should also notice that the change of volume, which is the product of alpha, beta, gammas, the determinant of each of these ui's, that's also extremely close to 1. And later, I will assume that that product is 1 as well. Right, but not all the time. Now, the condition that the middle eigenvalue is 1 is necessary for there to be a rank 1 connection, identity plus A tensor n, from the identity matrix in SO3 to SO3 U of theta, any of the UIs actually. And it's been identified in the pioneering work of Dick James and his co-workers as being associated with extremely small hysteresis in some alloys. However, in this alloy, even though lambda 2 is very close to 1, the hysteresis is large. Okay? So now maybe I should just explain for those of you who are not familiar with this sort of thing. So what's the importance of matrices of A tensor n, rank 1? So the key thing is that if you have a gradient which is, say, has the value A above some plane with normal n, and B, which is another constant matrix, above the plane, then the Hadamard jump condition tells you that A minus B is some vector A tensor producted with the normal. So, this is an essential condition of compatibility for making interfaces between phases. So the fact that you can make a rank 1 connection from the identity to SO3U, what that's saying is that you can make an exact austenite-martensite interface, which is not usually the case. Usually there's no rank 1 connection from the austenite to the martensite. But in these special middle eigenvalue 1 alloys, you can make such a rank 1 connection. So then you can calculate what they are, which starts to get a bit messy. So the 6 wells, right? So we have the identity and the 6 wells, and there's exactly 2 rank 1 connections to each of the 6 wells. Okay. And they're given, and they're of the form identity plus A 2i minus 1 tensor n 2i minus 1, and also 2i. Now in the case I equals 1, so now we're doing the rank 1 connections to the first well, SO3U1, they're given by these formulae. Okay, so A1 is A plus, and A2 is A minus, N1 is N plus, and 2 is N minus. And you see that they're given explicitly in terms of, well, the vectors E1, E2, E3, they're unit vectors in the 1, 2, 3 directions. And then we have the two alpha and beta, the two deformation parameters. Remember, I assumed that gamma was equal to 1. Okay, so they're explicitly given by these formulae. Now, for I bigger than 1, you get the other ones by noting that you can pre and post multiply by Q and Q transposed, where Q is in the qubit group. And then you get identity plus QA1 tensor QN1, which is another rotation times QU1 Q transpose, which is one of the other variants. Okay? So that gives you another rank 1 connection from the identity to the wells. And in fact, for each I from 1 to 12, there are exactly 2 rotations Q in P24, such that AI tensor Ni is QA1 tensor Qn1, and one of them gives AI is QA1 and Ni is Qn1, and the other gives AI is minus QA1 and Ni is minus Qn1, which of course doesn't change the tensor product. Okay. Now in particular, let's look at the sum of AI tensor Ni. So we've got these 12 matrices, rank 1 matrices, AI tensor Ni. So by this discussion, in fact, you can represent it as 1/2 of the sum over Q of QA1 tensor Qn1. And you see this expression is invariant to pre and post multiplying by Q and Q transposed. And therefore, QF, Q transposed, is just F for any Q in P24. And from that, it's a simple calculation to check that it has to be a multiple of the identity, right? But you can also work out what the trace of F is. That's because the determinant of U, which is alpha beta, is 1 plus AI dot Ni. And of course, the trace of AI cross Ni is AI dot Ni. And for that, in that way, you get an explicit formula for F, the sum of the 12 AI tensor Ni's. It's 4 alpha beta minus 1. So, in particular, if alpha beta is 1, which it very nearly is, then you have that the sum of these 12 matrices is 0. Okay? So the identity is in fact 1/12 of the sum of identity plus AI tensor Ni, right? So that the identity then belongs to the convex hull of these 12 matrices, identity plus AI tensor Ni. So here's the picture then. So here, energy wells SO3 times something are represented by circles. Of course, they don't look like circles, but that's the way they're represented. So the middle one is SO3, and of course the identity belongs to SO3. We could have taken any rotation on SO3 and you get the same picture. And now we see that there are exactly 12 matrices, 2 on each well, that are rank 1 connected to the identity. Okay. So we have these 12 matrices. There were 12 colors in the picture. That's not a coincidence, of course. And here's a lemma. So if these inequalities hold, then there's no rank 1 connections between any pair of these xi's. So you can't make an interface between any of these 12 gradients. And in the case when alpha beta is 1, that condition is equivalent to alpha not equal to root 2. And of course alpha is nowhere near root 2. Alpha is pretty close to 1. Okay, so here then is the rough sort of proposed explanation of why we see such strange things in here. So the high temperature cubic austenite phase transforms to the martensite by means of exact austenite-martensite interfaces. So this is what we believe happens. The deformation gradients in the martensite are approximately equal to those in this set K consisting of these 12 matrices. And thus they've got a complex structure because you can't make an interface between any pair of them. Okay? And that's why we see such an unusual picture. And this is supported experimentally by observed very small changes in orientation of each variant over the grain. So within a difference of 1.1 degrees, say for variant 9, so these are you see the ninth variant is more or less has the same orientation everywhere. Also the grain boundary is hardly deformed at all, experimentally. So here's a better picture of the 12 variants. So each one has a different color. And so roughly speaking, say in the green regions you have variant 6 and so on. And so a huge amount of work involved, of course, in doing these pictures. Okay. Right. So then, given that you can't make interfaces between these 12 matrices, what can you do? How can you describe a sort of microstructure when you don't have any interfaces between the gradients to work with? So almost the only way that we know how to do this is through what are called TN configurations. So I'm going to try and explain what TN configurations are. So I'm going to do this in arbitrary dimensions. So now this is sort of mathematical. So we're going to have it doesn't matter what the dimensions are. So we have a compact set K of n by n matrices. And so we can define the convex hull, the polyconvex hull, the quasi-convex hull, and the rank 1 convex hull essentially in the same way. So the convex hull is the usual convex hull, finite combinations of things in K. And you can represent that in the following way. It's the set of matrices A such that phi of A is less than or equal to the max over K of phi for all convex phi. Okay, now let's maybe go to the rank 1 convex, the next easiest one to explain. Okay, it's exactly the same, except that you replace convex functions by rank 1 convex functions. And rank 1 convex functions are ones which are convex in the directions of matrices of rank 1. Okay, so that's okay. So now, what about polyconvexity? So polyconvex functions are ones which are convex functions of the minors of the matrix. And so the same thing, except now you've replaced phi by polyconvex phi. And finally, quasi-convex functions. Well, that's a bit of a problem. So I don't intend to explain what quasi-convex functions are, but quasi-convexity is the central convexity condition of the multidimensional calculus of variations, right? And the thing is, and it's not very well understood either. So the thing is that convexity implies polyconvexity, implies quasi-convexity, implies rank 1 convexity. And so these hulls are oriented the other way. The smallest is the rank 1 convex hull. The one we would really like to know is the quasi-convex hull, and that's contained in the polyconvex hull, which is contained in the convex hull. Okay, and what's more, I want to talk about gradient Young measure. So a probability measure having compact support is a homogeneous gradient Young measure if when you act on a quasi-convex function, it's bigger than or equal to phi of the center of mass. So nu of phi is the integral of phi of a d nu of a, if you like. And nu bar here is the integral of a d nu of a. So it's the center of mass of nu. And it's a laminate if this holds for all rank 1 convex functions. And there are more rank 1 convex functions than there are quasi-convex functions. And we're going to be particularly interested in finite gradient Young measures and laminates. And those are measures which are finite convex combinations of Dirac masses. And so you think of these as corresponding to microstructures formed from gradients AI, each one taken with a volume fraction lambda I. So it's a way of thinking of microstructures. Okay, so what's a Tn configuration? So an ordered set of n distinct matrices, x1 up to xn, without rank 1 connections, forms a Tn configuration if this sort of picture holds. So first of all, there's a P, which is the sort of the center, the first point, if you like. Now, each of these matrices Ci has got to be rank 1. So you go from P in the direction of C1 until you get to P plus C1. And then you go a bit further and you get to X1. All right? So that's why this kappa 1 here is bigger than 1. Right? And then from P plus C1 you go in the direction to X2 in this rank 1 direction C2. And then you go a bit further, you get to X2, and you continue like this. And the point is, you've got to get back to P. So informally, how does this enable you to construct something? So this P here, you can layer it with X1 because they're rank 1 connected. So you form a very fine layering of P with X1, and then you get something which has gradient approximately P plus C1. And then you layer that with X2. And then you continue round and round and round, and you let all the fineness of the layers go to 0, and then you end up with a microstructure which is supported just on these n matrices Xn. Right? Okay, and Tn configurations are only possible if n is bigger or equal to 4. Okay. These are the explicit forms of the matrices. And here's a lemma. It says that if they form a Tn configuration, then setting Pi to be these. So these are the points. These are the points. How do we go back on this? Oh, there we go. Yeah. Okay, so what was I going to say? Yeah. No. Oh, okay. So going. So these are the points. The PIs are these points. This is P1. This is P2. This is P3, and so on. Right? So they're the points that appear here. And so all the closed line segments, in fact, everything in that picture that I showed, all the lines, are contained in the rank 1 convex hull of the n matrices. And in fact, any point in the rank 1 convex hull is the center of mass of a finite laminate that's supported on x1 up to xn. And in particular, if you look at, say, P, you can do it for all the other matrices, you get an explicit expression for a laminate which has center of mass P. And it's given by this combination of Dirac masses. The beta i's are 1 plus minus 1 over kappa I. The kappa i's were the numbers that were bigger than 1 in the picture. Okay, so this is essentially a standard result. Okay, now, following Kirchheim, this is less standard. We're going to say that an ordered set x1 up to xn of at least 4 distinct matrices without rank 1 connections forms a degenerate Tn configuration if there's a P and Ci's such that each Xi is P plus Ci. So they go out radially from P in the direction of matrices of rank 1. And so each Ci has to have rank 1, and 0 has to be in the convex hull of the n matrices. And you can prove a similar result to the one I mentioned before, so that if they form a degenerate Tn configuration, then in fact all these line segments are in the rank 1 convex hull, and if 0 is the sum of lambda I Ci, it must be for some lambda I because it's in the convex hull, but any such convex combination, then nu is some lambda I Dirac mass at Xi is a laminate with center of mass nu bar. And how's it done? Well, you perturb it so that you get a Tn configuration. So you do it in this way: Xi epsilon is Xi plus epsilon some lambda j is Cj from 1 to I. And then you check that that's a Tn configuration, and so you know that P is in the rank 1 convex hull of the Xi epsilons, and then you let epsilon go to 0. So that's the way it's done. All right. Okay, so now let's go back to our matrices. We have 12 matrices, x1 up to x12. They have no rank 1 connections, and an NR3. So the first thing is, a little bit sort of interesting, is that provided these conditions hold, these are the ones which I wrote down before, which says that there's no rank 1 connections between the xi's, then there are no Tn configurations in K. So how do we do this? So it's equivalent to show that there's no Tn configuration in the set K hat. So let's get rid of the identity just by subtracting off x from everything. Right? So it's equivalent to show that if I let Zi be Ai tensor Ni, then there's no Tn configuration in K hat. Well, suppose that there was such a Tn configuration, then it would be some ordering of things from Ai tensor Ni. Okay, so A1 hat tensor N1 hat up to An hat tensor Nn hat, and the Ai hat tensor Ni hat are some Aki tensor Nki. There's some ordered subset of K hat, right? So now, and we've got a corresponding point P. Now P, remember, has to, well, if it's a Tn configuration, it has to be in the rank 1 convex hull. And the rank 1 convex hull is contained in the polyconvex hull. But the polyconvex hull is known to have the following form. It's the set of matrices such that Ta is in the convex hull of Tk hat, and T of B is the set of minors of the matrices B. Here's the 1 by 1 minors, here's the 2 by 2 minors, and here's the single 3 by 3 minor. Now, of course, when you have a rank 1 matrix, the cofactor matrix is 0, and the determinant is 0. And so therefore, you see from this that in fact, a K hat PC is the convex hull of K hat intersected with the matrices which have cofactors equal to 0. And so that tells you that since P is in K hat PC, it has cofactor 0, and so it is a tensor product. It's A tensor N for some A and N. Okay, so here's the picture then. You have P, which is A tensor N, and here I've got A1 hat tensor N, N1 hat. I've just drawn part of the supposed Tn configuration. And now you see that A tensor N is rank 1 connected to A1 hat tensor N1 hat. So from that, it has to be the case that either A is parallel to A1 hat or N is parallel to N1 hat. And similarly, P is rank 1 connected to An hat tensor N hat. And so A has to be parallel to An hat, or N is parallel to Nn hat. Okay, that's what's written here. But we know that A1 hat is not parallel to An hat. That was what this lemma showed. And also N1 hat is not parallel to Nn hat. And so the only options are that P is a multiple of A1 hat tensor Nn hat, or n hat tensor n1 hat. And the constant lambda can't be 0 because these matrices are not rank 1 connected. So let's suppose, for example, that P was the first case. The other case is just the same argument. Then you write P2 is a convex combination of this P and A1 hat tensor N1 hat. So here's the explicit form of it. All right, but P2 is rank 1 connected to A2 hat tensor N2 hat. And here we have P2 is of the form A1 hat tensor something. And A1 hat is not parallel to A2 hat. So therefore, this vector has to be parallel to N2 hat. So that tells you that N hat and N1 hat and N2 hat are collinear. Okay? And then a similar argument, fooling around over here, has to show that AN minus 1 hat and AN hat and A1 hat are collinear. Okay? But then you do a horrendous calculation to check that under the assumed conditions it's not possible for those two things to happen simultaneously. Now, well, that's the negative thing. There are no Tn configurations. However, there are degenerate Tn configurations. So now, if alpha beta is equal to 1, then K forms a degenerate T12 configuration with P as the identity, and all the line segments from identity to identity plus AI tensor Ni are in the rank 1 convex hull. So that we already know why that is, because all you need is that the identity, well, that 0 is in the convex hull of the AI tensor Ni, but it is. It's the sum of them. It's 1/12 of the sum of all these, right? So we already know that's the case. And actually, it turns out that there are other degenerate Tn configurations, at least for any n between 9 and 12, and they're contained in the union with, well, other, yes. So the it should say with KRC, with the union of these line segments in KRC, and the corresponding laminates have volume fractions lambda I that are not all equal. So even for n is equal to 12, you can find a degenerate T12 configuration without the volume fractions all being equal as they are in the case from here. However, if alpha beta is not equal to 1, there's not even a degenerate Tn in K. Well, so what we would really like to determine is what KQC is, because that would give us that would give us a lot of information about the possible microstructure. So, I mean, a natural conjecture would be that for alpha beta is equal to 1, that the quasi-convex hull is equal to the rank 1 convex hull. In other words, is equal to all those line segments joining the identity to identity plus I tensor Ni. And then maybe since there's if alpha beta is not equal to 1, there's no degenerate Tn's, then perhaps KQC is equal to K when alpha beta is not equal to 1. Now, usually when you there's really only one thing we know how to do to determine what the quasi-convex hull of something is. So you sandwich it between the rank 1 convex hull, which is smaller, and the polyconvex hull, which is bigger, right? And so in order to prove something like this, if indeed it's true, then you would, I mean, the natural thing to do is to show that the polyconvex hull contains these. But the polyconvex hull is larger, actually, because the identity turns out to be a relative interior point of the convex hull in the set of matrices like this with A dot n equals 0. So you can't do that in this case. And that was also the case for a similar 2D example, which was considered by Kierkegaard. So where are we in summary? So what more can we say about the microstructure? Well, here it is again. I mean, exactly, how you see a Tn configuration it's not so clear, but you certainly have you have finer and finer parts of the microstructure. Now, so in some sense, it seems that what you're seeing here is an experimental approximation to an exact gradient, taking 12 values, having no rank 1 connections. Now you might think that that is impossible. Actually, it's known to be possible for 5 or more matrices. There's a 2x2 example of Kirchheim and Price of 5 2x2 matrices with no rank 1 connections and an exact gradient taking each of these 5 matrices on a set of positive measure. It's so amazing. There's somehow no interfaces. You can make no interfaces, but you can find such a thing. Now, whether that's possible here is not clear. In fact, if alpha beta is 1, then we can show that there's no exact gradient which is equal to the identity on the boundary, taking these 12 values xi. So, so that's done using some stuff on quasi-regular maps. Now, in fact, and this comes back to the remark about hysteresis at the beginning, one can observe some exact interfaces here. So, for example, probably there, you see there's an exact interface between this light grey one and this lighter grey one, right? Now, so the fact that you've got an exact interface there shows that it can't be stress-free. Right? So that's from the mathematical point of view, the gradients in these two things are incompatible. However, if you look at these 12 matrices, you can sort of you can take any pair of them and explain and quantify how compatible they are. So you can do that by saying, well, suppose I take one of them and then the other one, and I rotate in the reference configuration through an angle theta. What angle do I have to rotate by in order to make them exactly compatible? Okay. And so it turns out that there are some pairs here where the angle is very, very small. So there are some pairs of variants which are very nearly compatible, and they're the ones that you see here, for example. Okay, finally, somewhat similar microstructures arise in a probabilistic model, which I developed with Pierluigi Cesana and a probabilist from Oxford, Ben Hambley. And power laws arise in that model. I'll explain what the model is in a second. As they do in this alloy. So you can look at the number of plates of length L, and you find that the number is proportional to L to the 2.6, and that works over a very wide range of grain sizes. So I just showed one of these grains for which he sliced it with a hot wire and did all this stuff. Okay, but he did it with many grains, so you can imagine the amount of work. So anyway, what is this probabilistic model? Okay, so this is a two-dimensional version of the model. It's interesting in itself. So it's a caricature of the nucleation of multicytic interfaces. So first of all, we take a point at random from this. Okay, so in this case, first of all, instead of having, say, 12 possible orientations, I'm going to have 2, which is horizontal and vertical. Okay, so I choose, first of all, a nucleation site here at random, okay? And now with, say, probability 1/2, I choose an interface which is horizontal, and probability 1/2, I choose one which is vertical. Okay? So I choose a horizontal one, say, okay? And now I take another nucleation site at random, and again I choose with probability 1/2, either a horizontal interface or a vertical one, right? So suppose I choose a vertical one. Now I'm only allowed to go as far, well, I can go to the boundary, but I'm only allowed to go as far as the preceding plate, okay? And then you continue like this, okay? And then you get a picture like this for two directions, okay? And for 4 directions, you get a picture like this. So these pictures are not so completely unlike what you see in that microstructure. So probably what we're seeing is a complicated combination of factors relating compatibility and so on, and things like TN configurations, and a sort of nucleation process that that happens a bit like this. Okay, that's all.
Quick question. Questions or comments? Yes.
Thank you very much for this very nice overview and bringing us back to the TN configurations. So like in the theorem about the degenerate TN configuration, we were saying that the second part of the theorem is true for n from 9 to 12. So
Yes.
what happens to n equals 1 to 8?
I don't know. I'm not saying that there aren't ones. Well, of course, you need at least 4. But between, I don't know whether there are. I mean, the way it's proved for 9 to 8 is because you look, I mean, the space of matrices is 9-dimensional, but here we have the trace is given, which makes it 8-dimensional. And so you can represent anything in the convex hull by Heriot-Watt's theorem as a convex combination of 9 things. And that's why you get the 9 from. But maybe you can do it with less. Well, I doubt it. Well, I mean, maybe a bit less, yes, but I doubt if you could get down to 4, for example.
So for this T12 configurations, is it true that for each interface, you can have one variant on one side and a finite configuration on the other side?
Well,
it's like a fractal.
Yes. So I mean, essentially, okay. So there's 2 possible situations. The first is when there's an exact gradient which takes these 12 values, which is sort of doubtful, and we know is not the case when you have this boundary condition. But if it was the case, then that's exactly what you would expect. You would expect that you had regions where you took one gradient, and then on the boundary of that region you had a fractal of the other gradients. But maybe that one also, of course. Okay. So actually, with Carstensen in a paper which has been going for decades, actually, we tried to discuss, what generalizations of this Hadamard jump condition when you have just Lipschitz maps, right? And so you can have these fractal interfaces. Now, if it's the other case is when there's no exact gradient, and then you have at least mathematically an infinitely fine microstructure. Now, of course, in practice, no microstructures are infinitely fine, and the reason they're not infinitely fine is because there's energetic contributions due to the interfaces that are not in the model, right? Which will stop the microstructure refining past a certain limit. So in practice, you don't see an infinitely fine hierarchy of scales, but it'll go down to a certain scale.
All right. Any other questions? Okay. Well, if not, let's thank you.